Bismillahirrahmanirrahim. Welcome, dear students, to the platform of Quanta Publishers. This is lecture series Teach Yourself, and today our topic is about the differential operators. Here is the definition: the quantity whose operation on a function gives a new function is called operator. When some operator operates on a function, then it will generate some new function. Then this quantity that will operate on some function is known as the operator. And operator always operate on some variables. Here we introduce a differential operator known as the del operator. It is written as, here in this equation you see on the left hand side, del is expressed by this symbol, and del is a hybrid operator. It have two characteristics. It have a characteristic of derivative as well as of vector quantities. That is why you see on that symbol there is a arrowhead that represents that this del operator have a properties of vectors. So on the right hand side you see in Cartesian coordinate system we can express that the value of del as partial over partial x into I plus partial over partial yj plus partial over partial z in k, where I, j and k represents their x, y and z direction. Let us consider some scalar function, say u and v. And if we want to apply this del operator on these scalar functions u and v, then it can expressed as del of u and del of v. Now this del of u and del of v will become a vector function. This is an important thing over here, that we choose a scalar function and apply a del operator on these scalar function, and that del operator transform these scalar functions into a vector function. Here in this lecture we will see the three properties of these del operator. The first one is the gradient of a scalar field, the second one is the divergence of a vector field, and the third one is the curl of a vector field. First of all, we will discuss about the gradient of some scalar field. Here is the definition: the operation of del on scalar function is called the gradient. Here we choose a scalar function u and apply a del operator on u. Here you see that del of u. It can be written as gradient of u, and now it will become a vector quantity. Transformation from scalar function into a vector function. Here is an example. If we take the gradient of V, means the rate of change of electric potential, that becomes equal to electric field E. Here you see that becomes equal to electric field. The value of del from the above equation, we can write it over here, del of u. So first bracket is relevant to the value of del, partial over partial xi plus partial over partial y into j plus partial over partial z into k, and here is the u, the scalar function. When we attach this scalar function into that bracket, it can be expressed as, here you see that partial u over partial x plus partial u over partial y plus partial u over partial z along their respective I, j and k unit vectors. Now, what is the physical significance of this gradient function? As we know that when we apply the del operator on this scalar function u, it becomes a vector function. So here you see that it becomes a vector field. And vectors have two main properties, direction as well as magnitude. First one is the magnitude of this new vector del u is equal to the maximum rate of change of u, and the direction of displacement along which the rate of change is maximum. Let us consider we have a surface here, and here is a scalar function, and if the scalar function, and we travel from this point to this point along horizontal direction, there is no change in scalar function over this surface. And if we write its derivative in general format, it can be expressed as du divided by dr, that is rise over run, is equal to 0. If the slope becomes equal to 0, then we can conclude that that scalar function u is constant. And if we choose another surface over here and we transform this scalar function from this surface to this surface, then the maximum rate of change is always perpendicular to the first surface, means along the normal unit vector direction. If we travel in this direction, then this scalar function will have the maximum rate of change. So we can define here the normal unit vector as, here you see that normal unit vector will becomes equal to del of u, means the new vector, and divided by its magnitude. So by using the concept of gradient, we can find out the rate of change along the respective direction. The second one is the divergence of a vector field. When the operator del operates on some vector function, here you see there is a vector function, and if we take the dot product of del with that vector function, then it becomes a definition of divergence of that vector field. Let us consider we have a vector and its component are vxi plus vyj plus vzk, and then we take the dot of that vector with the del operator expressed as del dot v, and can be written as divergence of v. By plugging the value of del over here, the first bracket you see, it represents the value of del, and then here is a dot, and the second bracket represents the value of that vector v. And we know from the dot product, as we see in our previous lecture, that only the product between the similar vectors will remain, and the dot product among the different unit vectors will vanish. Here you see I dot j, j dot k, k dot I is equal to 0, and a similar unit vector, the dot product will retain. So we choose partial vx over partial x, because that product will retain, I dot I will become equal to 1, and similarly partial vy over partial y plus partial vz over partial z. What is the physical significance of this divergence? Here you see, now when we apply the del operator on some vector function, then the dot product on right hand side will become a scalar quantity. So the scalar quantities have some magnitude, and here you see that the divergence of that vector is the limiting value of the net outward flow of some physical quantity like fluid or electric flux through some surface area of a unit volume as the volume approaches to 0. First, keep it in mind here, the volume approaches to 0 means if we take a dot function or the point function and take its divergence, and that divergence is through some area, so give you the outward flux point function. So here are example from the Maxwell's equation del dot d. If we take the del of electric displacement vector, it will generate rho over epsilon naught. And if we take the divergence of magnetic field del dot b, it will become equal to 0. And the third one here is about the curl of a vector field. Now, if we take the del operator and apply it on some vector function and take their dot product, then this new function will known as the curl of a vector field. It can be expressed as del cross V or written as curl of V. In the cross product, in our previous lecture, we have seen that we can eliminate the cross product by using the determinant properties. So here you see a determinant del cross V is equal to first row will represent their respective I, J and K direction. Then second row express the value of that del operator, partial over partial x, partial over partial y and partial over partial z. And the third row represents the vector V and its component Vx, Vy and Vz. We know how to eliminate this determinant, and solving this determinant we have the final equation like this. Here this right hand side is a vector quantity, it is not a scalar function. Practical significance of this vector function is, number one, the magnitude or whose component in the direction of unit vector n is given by the line integral of some vector v along a closed path per unit area enclosed by, provided the area being very small. So we can express curl of v dot n as a line integral of that vector quantity v dot dl divided by a. Here area is very small. So if we multiply this dA on left hand side, we will have this, and by the definition of normal unit vector we can write it as dA vector. So the dot product here is among the curl of v dot dA. This will become equal to the line integral of that vector function v. So this is the relation among the line integral and the curl of a vector, and that curl of a vector will give us the rotation about that vector field. Thanks for watching. We will meet in the next lecture.